zeros, like what Jung has been doing in his course. Okay, this filters is a feedback type of filters. You implement this filter using feedback, and h of z can be described as this: 1 over 1 minus summations from n1 to large N of a n z to the minus n. So this large N is the highest order of the filters. Okay, this is the order of the IIR filters. And for speech, N can be anywhere from 10 to 20. Okay, for images, take a look at this. All we're doing is N equal to 1. Okay, and that's all I need, because all I care about is how my neighbor look. That's all I care about, how my neighbor look. Because if I can predict myself from my neighbor, most of the time I'm going to be doing okay. So for images and videos, we usually use this AR1 model, and then A1, which is the coefficients here, is called rho, or the autocorrelation coefficients. And for images, people pick 0.95. Okay, that's just the way people use it. So let's see how can we visualize this AR1 image model. Okay, for x of z, so x of z, which is the output of this box, okay, is just simply h times w, right? So we learned this from Mandarin course, right? Multiply in z domain or frequency domain, and if I substitute everything in, I have w of z over 1 minus rho z to the minus 1, because this is the AR1 model. Okay, now simple manipulation give me x of z is equal to w times this, right? So w times this. Okay, so I will have wz plus rho times z minus 1 x of z. Okay, now how do we get back to the time domain? Inverse z transform, right? What does this give us? X of n. This, what will this give us? W of n. What does this give us? Rho times, right, x of n minus 1. Okay? So in time domain, okay, so it's just the intermediate step is to take all the x together to one end, noise to the other end, and then do the inverse, and then you will have x of n is equal to w of n plus rho times x of n minus 1. So this is the way, so intuitively, this is what happens. You are sitting at index n, you have about 95% similarity with your neighbor, right? And then there's this little noise component, right? This is the variation. This is controlling how far you're away, right? So most of the time, you're very similar to your neighbor. Okay, you're only off by this small little noise component. That's all. So that's what AR1 image model looks like. Okay. Now maybe I could do if I can get out and do something real quick in MATLAB to show you. I want to show you the visualization of such an image and see how it looks like, right? So this is part of your exercise, but I already did the exercise before you. So I'll give you an idea of what to expect, okay? So y is AR, this is the functions in MATLAB, and if I pick this, the correlation coefficients, rho, and I'm going to put down 0.95, which is what I just showed, okay? This is the size of the image, and this is what being generated using the recursive formulas. Okay, so I generate y noise, right? And I feed it through that filters, right? And I try to display it as an image for you to see. So if I do y, okay, come on, okay, and then let's display. Should not be that slow, but anyway. So this is how it looks like. Okay. So you typically this image is pretty smooth. Okay, it cannot generate the strong edges like we see in regular images, right? Because most of the time you are 95% the same as your neighbor. There's only that small little fluctuation. So it's hard to come up with a model that can capture edges and stuff. Okay, but if you this is the best model that we have so far. I mean, there's just nothing else that actually works. Okay, so now if I put we can play around with correlation. For example, if I put 9999 like this, you would expect what? A smoother image, right? Or maybe even the same, right? Now, so yeah, true. I mean, it looks smoother, okay, and a lot more similarity between components. And if I choose a very small number, okay, if you want to see white noise, what do I put here? I just want to see white noise. 0, right? Because if I put 0 there, there will be no more recursive. X will be equal to W, right? So this is white noise. That's white noise. There's no correlation whatsoever. You don't see the relationship anymore, right? So this is how we model an image using stochastic processes. Okay?
Excuse me, what does AR mean?
AR means autoregressive. We need this slide because we need to evaluate the performance of our system. Right? When you do compression, when you throw information away, you need some kind of similarity criteria, okay, to judge the performance level, okay, of your system. So the most popular similarity measure is called mean square error. This is what we use all the time in image and video coding. Okay, and it's defined as the L2 norm, okay, which is 1 over n summations over I going from 0 to n minus 1, which is all the pixels that you have. Okay, and then you have the expectations of xi, which is the original signals, and then original pixels, and then this is the reconstructed pixels. Take the difference, take absolute value, everything squared. Okay, and you do it throughout the entire image. So in image you have 2 dimensions, so you can break this 1D into 2D, or you can just vectorize them and then do it in 1D. Okay? If you have 2 images, that means they are both deterministic, right? There's no randomness to it. You can drop the expectation. So the expectation is there when we model the signals, or we feed our system with some kind of signal models. Okay? But if you have a real image, like what I showed you before, you simply just take the 2 images, every pixel, you do this operation, absolute value square, summation, scale, and that's it. That's your mean square error. It tells you how far you are away. Certainly the lower the number, the better it will be. Right? A very similar measure for MSE is called peak signal to noise ratio. Okay? And all you have to do is take that MSE values and feed it into this formula. Okay? And voila. This is the maximum peak to peak. And M is the maximum peak to peak value of the signal. If it's an 8-bit image, then you can put 256 here or 255 here. 255 square here, because 0 is the minimum and 255 is the peak. Right? So you can put it there, take 10 log base 10, and you have signal to noise ratio. Another measure is called the mean absolute difference, or it's just the L1 norm. Okay? So instead of squaring, you just take the absolute value. Okay? And again, you do the summation over the entire signals. You scale by 1 over n, which is the number of pixels.